Yeah, so first question, counts, and then find the MLE of using the notation. So here we have counts for each of the categories, say A, B, and C, D for category, and then the probability for each category occurred. And we have 1997, say, occurrence for this, so say category A, and then each of them has the probability of that. So to find the MLE of that, we need to first construct the joint likelihood. So yeah, so T1 plus T2, T3, T4 equal to N. And here's the joint likelihood. So we just take the product for each of the probability for each of the occurrence. So we have 0.25 multiplied by 2 plus theta raised to the power of 1997, or T1. That is the number of occurrence for category A, say. And then we have 1 minus theta raised to the power of 0.25 multiplied by 1 minus theta raised to the power of T2. And then the same for category C and category 3 or category 4. So you take the product. So this will be the joint likelihood for the distribution, for this PMF particularly, and raised to the power of their corresponding occurrence. So this will be the likelihood. And then yeah, we just basically follow the template. We take the log of the joint likelihood function. So log of product is the sum of log. So yeah, one thing is that the 0.25 is for each of the terms. So here we just raise to the power of n directly. And then we take the log, so we have n log 0.25, and then T1 log 2 plus theta, and then etc. for all the terms here. Once we have the log likelihood, we just take the partial derivative, or the derivative with respect to the only unknown parameter in this PMF, which is theta in this case. So derivative of the theta. This is the constant, and then T1 over 2 plus theta, T2, T3 over 1 minus theta, and then T4 over theta, and set it equal to 0. And now basically we just solve for the only unknown, or solving an equation. We have one equation, one unknown, and and then once we simplify, we have a quadratic equation here. And we just take the formula, and then we have a closed form solution for the theta. And actually it's a two solution. One is plus and minus for this part. And since the question, there's no constraint on the parameter, so we can leave it as this for the solution. Question or comments? Yeah.
Theta, it can't be negative, right? Because that would result in a negative probability.
Yes, that's a good concern, but for now we don't know whether this part is greater than that, right?
Okay.
Maybe in the number, maybe this will be greater than that. It will become a negative, but so far it's just using the notation, so we don't know yet. Yeah. But maybe when we apply the numbers, maybe it will be greater, and then we should remove that choice. Okay, part B. So find the Fisher information. Again, back to the probability for each of the category. So we have the probability for each of them, and then we take the log. So log 0.25 plus log 2 plus theta, and then same for each of the category. And then we take the first order derivative. So 1 over 2 plus theta, and then, yeah, take the derivative for each of the 4 components, take the square for each of the 4 components. And then we use there are different ways that you can get the Fisher information. So here I just use the square and then take the expectation. So the expectation is that this component multiplied by the probability of category A plus this component multiplied by the probability of the say category B. And then, yeah, this is by the definition of the expectation. So we're taking the expectation of the square of the score. And this will give us the Fisher information, which will reduce to this. Yeah. And then for C, sample size and asymptotic variance. Yeah, so sample size is just the sum of the all occurrence, and then it will give us the n. For the asymptotic variance, it's just n multiplied by the Fisher information, take the inverse, where your zeta MLE is the one that we get from here. Or you can just use the zeta MLE as the notation. And lastly, to calculate the, okay, so the standard error is just taking the square root. And then, yeah, here you can just point it out that the zeta MLE is the one that we calculate in part A. And lastly is to construct the confidence interval for zeta, and then specifically using the data set, the counts here. So we can just first get the zeta MLE and then the Fisher information. So these two, the one that we calculate in B, C, and D. And then once we have that, we just use the zeta MLE plus and minus the quantile multiplied by the by the square root of the asymptotic variance. And that will give you the 95% confidence interval for your zeta MLE. Question or comments? Okay, problem 3 of homework 3. So, an independent observation, probability function, and Fisher information, MLE, asymptotic variance, and then confidence interval. So same template for as question 1. So this should be the discrete density, or the discrete or the probability mass function for the, I think 3 categories from the homework 3 of from the question from the homework 3. So again, we just take the log for the corresponding likelihood, take the derivative, and then take the square. And then we do the expectation for each of the components from the square of the score function. So yeah, the score is just first order derivative, and then we take the square, and then we take the expectation. And then, so same procedure. First component multiplied by the probability of category A, and then second component multiplied by the probability of category B, and then, yeah, and then when you sum them together, which is the definition for the expectation, and then that will give you the Fisher information. And this, when we simplify, and then we will have this. And for the asymptotic variance, it's just we multiply n to this, and then we take the inverse. So yeah, and then the zeta now can be estimated or can be replaced by the zeta MLE, the one that we get from the data. And then for the last part, we just construct the confidence interval using the zeta MLE plus and minus the quantile multiplied by the square root of the variance, the one that we get from here. And yeah. So same as question 1, except for a different probability mass function. Any question or comments? Okay, Kl divergence. So here we have the sample space for x. So x can be 0, 1, 3, and 5. You can also consider them as category A, category B, category C, and D, instead of just values. yeah, basically just 4, yeah. And then each of them, when under different theta or under different probability mass function, the sample, the corresponding observation have different different probability. For example, under this model, the probability that you observe at 0 is actually a 0.5, and then observe at 1, it will be 0.2, and then observe at 3 has this probability. And under a different probability, PMF, you will have different probability for observing the same 4 category or same these 4 values. And same another different distribution, you will have different probability. So each column should be sum up to 1. That represents your distribution, your probability mass function. So given the 3 different distribution, we are trying to calculate the Kl divergence for each combination of the 2 distribution. So 1 and 2, 2 and 1, and 1 and 3. Yeah. So to calculate that, we basically just plug in a number for the Kl divergence, which is has this formulation. So the Kl divergence from P to Q is the summation over all possible x for its sample space, which is 0, 1, 3, 5 in our case, or category A, B, C, D, or 4 categories for that. And then the probability for that observation multiplied by the log of the probability for that observation over the probability from another distribution of the same observation. So in our case, question 1 is for theta 1 and theta 2. So basically, we're trying to calculate divergence between this distribution and this distribution. So sum over all possible x is 0, 1, 3, and 5. So first, let's take a look at the 0. So probability of observing a 0 under the first model when theta equal to 1, we have probability 0.5, which is this one here. And the same for the numerator in the log. And then for the second model that we are trying to compare, which is theta equal to 2, the probability for observing a 0, it's 0.3. So this is this denominator here. And then we just sum over all possible x. So for when equal to 1, we have 0.2 and 0.3. So 0.2 and 0.3. So basically just plug in the number, get the look for the probability, and then calculate this summation. And that will give you the Kl divergence between probability, the first probability distribution and the second one. And then for B and C, or for 2 and 3, we just calculate 2 other different choices for the second one and the first. The second one and the first one. So the Kl divergence, the order also matters. So P from Q and Q from P, you'll get 2 different answers. And then from 1 to 3. So look up for the different number, plug into the formula, and then you will get your answer for that. That's for 1, 2, 3. Any question? Okay, if not, then for part 4. So verify that if the true distribution of a random variable x is given by theta equal to 1, then maximum of the expectation of the log probability is achieved as theta equal to 1. Yeah, so here is the expectation of the log of the probability. And when theta equal to 1, yeah, we just sum over all possible x, and then this is the probability distribution. Because we are talking about, or we're trying to calculate the expectation. Expectation for the discrete random variable is the sum over the probability multiplied by the function in here. So this is the probability under theta equal to 1 multiplied by this term here. And now we can just plug in the numbers for each of the theta. So when theta equal to 1, we plug in all the probability for, so this will be probability of theta equal to 1, and then probability of theta equal to 1. And when theta equal to 2, so this again is the probability of theta equal to 1, and then probability of theta equal to 2. And then same for when theta equal to 3. And now when you calculate the three numbers and then look for the maximum, and then yeah, you will see the maximum is achieved when the theta hat is equal to 1. Yeah, so basically just plug in the numbers in this formula, which is what the question is asking us to verify, and check whether when theta equal to 1, you reach the maximum for that. Any question or comments? Yeah, for this part, just mainly plug in the numbers. And for question 4, so continue from problem 3, this one. Assume the data are likely to be generated from any of the 3 distributions. This is actually problem 3, so from here. Yeah, in other words, theta can be 1, 2, and 3. Suppose 5 data points are observed. Find the MA of theta. Would your answer be different if the 5 data points are the other 5 numbers? So, yeah, first of all, let's see. Yeah, so based on the 5 data point here, the way to read this is that we have one occurrence for 1. Because our distribution, the support is only 4 categories or 4 numbers. So the way to read this is that we have one occurrence for 1, and then we have two occurrence for 3. And then we have 2 occurrence for 0, and then 0 occurrence for 5. Because we can only observe 0, 1, 3, and 5, but in the sample, we can observe them multiple times. So in this particular data point, we have 1 occurrence of 1, 2 occurrence of 3, and 2 occurrence of 0, and 0 occurrence of 5. And then we plug into the log likelihood. Let's see if we have that. Yeah, so here I plug in this table as the probability for the 3 distribution as a table, and then we plug in to the log likelihood. And then, so basically this function is calculate the log likelihood for the same data under the 3 distribution. But then we look for which of them has the maximum. So in this case, which we have 2 occurrence of 0, 1 occurrence of 1, and then 2 occurrence of 3 and 0 occurrence for 5. So we plug into our log likelihood, and then we evaluate it for 3 of the data, for 3 of the different distribution. And then we look for which of them has the maximum. So we can see that when theta equal to 3, this data set achieved the maximum log likelihood when theta equal to 3. And the question has a follow-up question. It's asking that we have additional 5 data points. So the way to read this is that we have 2 occurrence of 0, and 1 occurrence of 1, and 2 occurrence of 3, and 0 occurrence of 5. So basically, even the orders are different. Actually, this is the same thing as our first data point. So without calculation, we should actually get the same answer, because this is the same count number for each of the 4 categories. So we can do it again. So yeah, the data set is basically the same. We still have 2 occurrence for 0 and 1 occurrence for 1, 2 occurrence for 3, and 0 occurrence of 5. So again, to calculate that, we will still have the theta MLE equal to 3 when it is maximum. And later on, when we have different counts or different data set, we will see that the theta MLE will be different. So any question up to this point? Yeah, so the trick here is that we need to convert the data into the counts, because that is what our likelihood is looking for. We need the corresponding counts to raise the power for that probability and take the log and then to find the log likelihood. So once we have this form of data instead of the individual counts, and then we can calculate the log likelihood and then look for the maximum. And then in this case, the two of them are actually the same. And now let's take a look at the second cases where we have 30 occurrence of 0, and 30 occurrence of 1, and 10 occurrence for 3, and 30 occurrence for 5. So basically we have a 100 sequence instead of 5 data point here. So under this data set, the question is asking what is the MLE for this data set under the 3 possible choice for the distribution, because it can only be 1, 2, and 3, just in this case. I mean in this homework. So now when we plug in the number for these corresponding counts, and then when we plug in to the log likelihood, we can see that for this particular data set, the maximum the MLE is actually equal to 2. So maybe we can also see this. Yeah, so you can see that the probability of getting a 0 and getting a 1 and getting a 5 is 0.3. So of course, in this data set, we have more counts for 0 and more counts for 1 and more counts for 5 and fewer counts on 3. So basically, it's just another way to say this thing here. But just by using the data, we also show that the maximum MLE achieved when it is equal to 2. And then for the other data set, we have 50 occurrence for 0, 20 occurrence for 1, and 10 occurrence for, yeah. And maybe it looks like this one, 50, 20, yeah. So I think this should have a maximum of, yeah, the theta MLE is equal to 1. So the trick here is that we need to first convert the data set into the counts, so observation to counts. And then, because based on the question, we only have 3 possible choice for the theta. So this, we just plug in this probability as a table for our, say, a searching algorithm or searching to search which one can reach the maximum MLE. And then we calculate the MLE for each of them and then find the maximum. And we can see that when the data, well, intuitively matching with the probabilities, we can see that the MLE is actually the same, or, yeah. Does it make sense, or if it is? Okay. Any other question or comments? Okay, question 5. So we have a sample of 100 data point, and then the frequency for each of the value is in this table. So we have 32 occurrence for 1, 19 occurrence for 2, etc. And then find the confidence interval for theta, and then it's under the geometric distribution. Problem 1 and 7 from homework 3. Okay, and then find the confidence interval for that for using the bootstrap. So we need 1,000 runs, and each of them generate 5,000. We need to generate 5,000 values of the theta MLE, and then Yeah. So, yeah, actually one thing is that when you calculate the MLE, you probably need to use this data set here. I think I generate this data using when set C equal to 1. So you can double check. If you run this two line, you should also get the same number as here. Yeah. But yeah, just to make sure you use the same data point to estimate your MLE first. Yeah. So here's the data point, and then we are asked for 1,000 bootstrap. And here we have the MLE for the geometric distribution. This is what you did for problem 1 and 7 on your previous homework 3. So you should have the same formula as this one. So this is what you derived last time. And here we're just going to use it directly. And also, I think you also derived the asymptotic variance in homework 3. And then we are just directly using that for here. And yeah, so this time we're just using as our codes to calculate that directly. And now we have the bootstrap. So the input is data, and then the number for your the number of runs. So input data, which is the one that is given here, 100 number. So we first calculate the MLE, and then we create a placeholder. And this one is just the estimated standard error, the square root of the asymptotic variance of the data. And then to run the bootstrap, we're going to run 1,000 simulation. So for each of the 1,000 iteration, we first generate 5,000 data point. And then based on the MLE that we estimate from the data. And then for each of the sampling data, we calculate the MLE. And then the MLE should be using the same function as what we derived for the geometric distribution. So in this case, we will have 1,000 numbers, 1,000 estimated MLE that is stored in this placeholder. Once we have that, here we plot the histogram, and then we show the two quantiles for 0.025 and 0.975. So the two quantile for the histogram, or the one that we calculate for the 1,000 MLE. And then we construct the lower bound and upper bound. And this are just direct application of the functions, which you can find it in the slides. And once you apply these formula, you will be able to get the confidence interval for the lower bound and upper bound. And lastly, we output or we print the confidence interval, upper bound and lower bound. So here we can take a look at the result. So this is the original bootstrap, which is the first question. And let's take a look. We have the 1,000 estimated theta, and also the two red lines, the one for, corresponding to the two quantile. And then the confidence interval will be this one. So any question up to this point? Okay, if not, then we'll just continue on the student type bootstrap. So this is another type to calculate the standard error of the theta ML of the MLE. So what is different from the last example is that MLE of the data, asymptotic variance, and then placeholder. For each of the 1,000 iteration, we still do the sample, and then we obtain sampling data. We find the MLE, but this time we also calculate the asymptotic variance for the sampling data. And then we use this formula to construct, I think maybe in the slides it's called delta, but this is the quantity that we are actually storing for the 1,000 simulation. And then we plot the histogram and the two red lines for the quantile. And lastly, we apply the two formula to calculate the confidence interval, the lower bound and upper bound. So, and then we print that out. So let's take a look for this one. We will have another histogram for our simulated, for our sampling data. And then this is our confidence interval for the theta MLE. Under this one, it seems like it's a little wider. And and this one, it seems like it does not cover the true values, and this one, it does. Yeah. But in fact, in practice, we don't know what is the true value, but we just have some different choice or different method to calculate the confidence interval. Yeah, but after all, basically just applying the procedures and then using the R code to do it, and nothing really fancy here. Question or comments?
Hey, so can you clarify the difference between the original bootstrap and the studentized one?
Sure. The only difference is that what information that we are storing. So for the, maybe start from here. So for the original bootstrap, we are actually trying to store the MLE for each of the sampling data. So we're sampling 1,000 data point. We have 1,000 simulation, and within each simulation, we sample a new data set and calculate the MLE. And each of the MLE, this MLE is the one that we store. So after this step, we will have 1,000 MLE, and then we use that MLE to estimate some following parts, the distribution. But the key difference is that we store the MLE, and then for the studentized variance, we actually store this part. So this is the difference from the estimated MLE to the true MLE. Or by true MLE, I mean the one that we calculate for the data, and then over the standard estimated standard error for also the one that we calculate from the sampling data in each simulation. So the key difference is that the data, the things that we store in each simulation are different. So one we store MLE, the other the studentized bootstrap. This is the thing that we store. So maybe it still does not make sense, but intuitively, if you think about it, actually we are using two pieces of information in the studentized bootstrap. So that also explains why this is wider. So the two pieces of information is that one we get from the P star, and then some variance, some information on the variance in the numerator. So the things that we store actually contain two pieces of information from the sampling data, whereas the first one only contains one piece of information from the sampling data. So of course we obtain more information. So maybe that is the underlying reason why it covers the true MLE, the true parameter in this case, and then it is also wider. So that is just some intuitive sense. But the key difference in terms of the two algorithms is that it stores different information in the algorithm. Does it make sense, or if it is still too confusing?
Somewhat.
Huh?
Somewhat.
Yeah. If you are really interested, besides just implementing the algorithm, I think I have another video that I recorded a long time ago regarding this, but you can look it up on my channel. Yeah, I have another video talking about how to derive this and then in detail. But if you are interested, you can take a look on that one. Yeah. But in terms of your question, what are the differences? That the pieces of information that we store are different in the two procedure, in the two algorithm. Yeah. But if you're interested in why, you can take a look at the other video that I recorded a long time ago. Yeah. I think in that one, I derive how to get the two procedure here. Any other question or comments? Okay, question 6. We have 5. Okay, I think I'll just skip this one because it's the same, just implementing the bootstrap for a different probability distribution. So basically, you just implement the same procedure, except you probably need different MLE, the formula, the one that you derive, and then the asymptotic variance. But for the bootstrap, the underlying structure is the same, except different distribution. So I will skip question 6 for now. And then for question 7, so a linear model, and then find the MLE of both theta and sigma. So we have two unknowns here. And y1 is denoted as theta xi squared plus xi epsilon I. And epsilon I is the one that it follows a normal distribution with normal 0 and sigma squared. And yeah, again, independent assumption. Question 6 and question 7. Okay, so this is the distribution for epsilon I. We are interested, or we also have a function for yi. And yeah, so now we are trying to get the distribution for yi. So the mean value for epsilon I is 0. We multiply by xi, so we have a xi multiplied by 0 as the mean, which is again a 0. And then we shift the mean by theta multiplied by xi squared. So we also plus a theta xi squared in here, and then resulting in a mean of theta xi squared of the normal distribution, which we inherit from the epsilon I. And then for the variance, we have a xi multiplied by epsilon I. So for the variance, when we do the multiplication, we actually enhance the coefficient by taking the square. So which is xi multiplied by epsilon I, it should be xi squared multiplied by sigma squared. And this is the variance. We also shift the variance by a constant term, but it has no effects on the variance, so then we are only left with xi squared multiplied by sigma squared. And this is the distribution, or the target distribution for yi once we inherit the normal distribution of epsilon I, from epsilon I. And we have two distributions here. And now we are trying to estimate the theta and the sigma. Then we are going to create or to construct the likelihood function and then take derivative and following templates. So any question up to this point? We just inherit normal distribution from epsilon I to construct the yi. Okay, once we have that, construct the likelihood function. We have an independent assumption, so product of 1 to n, and then the normal distribution, where yi minus the mean over square root of the variance. And under that, take the log. So log of product is the sum of log, and we simplify it to this. Take the derivative with respect to the first unknown parameter. We have two, so we first work on theta. And where is it? Here, yeah. Set it equal to 0, we can find that the theta MLE is equal to this. So you should solve the question or solve the parameter until your parameter can be expressed fully by the data point that you have. So there's no unknown on the right-hand side. So this is your theta MLE. And then solve for the other unknowns, which is the sigma. So again, from the log likelihood, take the partial derivative with respect to the unknown. Set it equal to 0, we have this. And then, yeah, so it seems like it involving a theta. But first is that we notice that the theta can be expressed by the data as well. So we can plug in the theta as the theta MLE, or the one that we evaluate from the data. Take the divided by n and then take the square root. It can only be positive. And yeah, so yeah, construct the log likelihood partial derivative with respect to the two unknowns, and then solve for the two unknowns. And then your final answer should be only based on the data. So yi and xi are data, and this one is also based on data, where the theta can also be calculated from the data. And then you have solved the MLE for the two parameters. Question or comments? Okay, question 8. So 2 sample and then 3 parameters. So x1 to n and y1 to m. And 2 normal distribution, again, keywords, independent. So find the MLE of 3 parameters. Based on the information, we first construct the joint likelihood. Because they are independent, so the product of the normal distribution for xi multiplied by the product of the normal distribution for all the yj. Because they are independent, so that you can take the products. And then some simplification and take the log. And the rest is just taking the partial derivative with respect to the unknown parameter. So first, with respect to tau. And then, yeah, so your tau can be expressed as some data point and then some one unknown quantity. And then we can leave it for now as this for now, and then see for the other relationship between the 3 unknowns. But this is not yet done. And also from the log likelihood, partial derivative with respect to mu, set it equal to 0, simplified and calculate the mu. And up to this point, it seems like the mu hat can be estimated from the data. Once we have that, plug into this one here, and then your tau can also be expressed in terms of data. So now we have solved for the 2 unknown quantity, and then look and then solve for the other 3, the last unknown. Partial derivative of sigma, set it equal to 0, and then simplify to this. We also have it also involving mu and tau, but we already expressed them in terms of the data. So just plug it in, and then we have our final solution as this. So the basic setup is that based on the data, and then we also have the keyword independent. Take the product for 1 to n to 1 to m, and then construct the log likelihood. From there, take the partial derivative with respect to your target parameter. And we have 3 in this case, so we have 3 partial derivatives. And yeah, so 3 equations and 3 unknowns, we should be able to calculate their solution. And finally, we also find out that their closed form solution for the 3 unknown parameter. Any question, comments? Okay, so this should be 9. Okay, survey and 3 members in the family. We observe counts of 35 for equal to 0, 20 occurrence for 1, 15 occurrence for 2, and 30 occurrence for 3. And model of 2 parameter, theta 1 and theta 2. And this is another PMF here. Find the MLE and plot the joint likelihood surface. Yeah, so again, same construction. For probability and taking the log. So we have the log and then construct the joint log likelihood. So the counts multiplied by each of the components. And then partial derivative with respect to both theta 1, individually for theta 1 and theta 2. So this is our log likelihood. take the derivative with respect to theta 1. We have that, set it equal to 0. And another derivative with respect to theta 2, set it equal to 0. And yeah, I think for this part we can just simplify it and then solve for the equation. So 2 unknowns, 2 equations, and you should be able to get a closed form solution for both theta 1 and theta 2. And they can also be expressed both in terms of T1 and T2, T3, and T4. Plot the function, find the Fisher information, confidence interval. Yeah, so you can just calculate the log likelihood and then create the 3D plots. So something like that, and then look for the particular range, and then it is possible that you get no log likelihood for a particular combination of theta 1 and theta 2. So and then you ask to construct that, and then for the Fisher information, just take the logs, second derivative, and then so take the log and then because now we're talking about Fisher information matrix instead of just a single value. So we have to take partial derivative with respect to theta 1 and then for theta 2. So this is the second derivative of theta 1. So twice derivative for theta 1 and twice derivative for theta 2. And then the derivative for theta 1 and then followed by theta 2. So we have the 3 components here. And now to construct the Fisher information matrix, we need to construct or to calculate the 1,1 entry for the Fisher information and the 2,2 entry. And the 1,2 entry and the 2,1 entry are the same. And then, but you need to construct the 4 elements from the partial derivative here. Once you have that, your diagonal elements will be your variance for your parameters theta 1 and theta 2. And then taking the square root of the diagonal elements and then using that as your standard deviation to construct the confidence interval. Any question or comments? If not, then this concludes all the homework 4. I'll just stop recording for now.